Hello, everyone. I'm Sean Buckley, Editor-in-Chief of Lightwave, and it's my pleasure to welcome you to today's Lightwave and HFCL webcast, Smaller and Faster High-Density Optical Microcable. During this webinar, we'll discuss the potential of how high-density optical microcable can enable enhanced fiber density in outside plant networks. To discuss these factors and how to strategize around them, it is my pleasure to moderate a presentation from an industry expert. Today we have Henson Toland, who's the Senior Product Development Engineer for Optical Fiber and Cable Business for HFCL. Welcome, Henson. But before I hand things off to Henson, let me quickly review our webcast setup for those of you who may be joining us for the first time or for the first time in a long time. I'll start with the Ask a Question box near the slide area. I invite you to feel free to ask questions during the event today. To submit a question, just click on that box, type in your question, and hit the send button. We will address your questions after Henson has finished his presentation. Now, in the event that you run into a technical problem during the presentation, you can call for help via the Q&A tool. Just describe your problem, hit the question submission button, and Matt, who is today's webcast technician, will be happy to help you out. Next, if you know of someone who might benefit from seeing this webcast or you just want to revisit the presentation yourself, this event will be available on demand from our webcast archive for the next several months. We'll send you an email with a link to the archive sometime in the next day or so that you should feel free to forward to your coworkers. In the archived version of the webcast will also be accessible from the webcast archive section of our website, which you can reach via our homepage at www.lightwaveonline.com. We'll also provide access to today's presentation, which you can take a look at if you like. You'll be able to download a copy of today's slides via the Event Resources tab you should see on your screens right below the Ask a Question box. Just click the tab to reveal the slide files. Finally, a certificate of attendance will be offered for those who want it. And with that, let's begin our look at high-density microcable. And I'm going to hand things off to Henson. Henson, the floor is yours.
Thank you, Sean. Diving into this. So I am Henson Toland. I am Senior Product Development Engineer within the Optical Fiber and Cable Business Group within HFCL. And today we'll talk about smaller and faster high-density optical microcable. So as a quick overview of HFCL, we're new to the North American market, but we've been around for quite some time. Established in 1987, HFCL's headquarters is in New Delhi, India. We do have 3 optical fiber and cable manufacturing facilities within India, specifically in Chennai, Goa, and Hyderabad. We do have regional offices in 7 different countries. Specific to our Hyderabad facility, we do have a fiber draw capacity of 12 million fiber kilometers per year, looking to expand that to 34 million by middle of next year. The cable capacity is currently 25 million, looking to bump that up to 30 million this year as well. So looking to expand our international presence, and I am here today to discuss microcable specifically. So as far as the webinar is concerned, like I said, we're going to talk about microcable and jetting. We're also going to look at the application considerations, and then dive into a little bit more into the cable design considerations and talk about some of the traditional product offerings that are out there, specific to HFCL, and then also looking at some of the advancements made within the industry, but again, it's more specific to HFCL. And some of the pictures that we have here, the top left one is a makeshift jetting track right in front of our fiber draw facility. And then off to the top right is more of our standard IEC spec jetting track, the N by 100 meter specifically. And then the couple of different cable constructions that are shown here at the bottom. The bottom left is more of a small fiber count, loose fiber type of design, like a small microcable or blown unit type of design. The bottom middle is a typical intermittently bonded ribbon unitube type design. So very similar in terms of construction as the former, but more dedicated to high fiber count designs. And then the bottom right is a microcable, a traditional loose tube microcable within a duct, and we'll touch on that as well. So going on to the next slide, microcable evolution over the past 25 years. You can see here how everything has drastically changed since really around 1999, 2000, that time frame, going from 2 fiber 2 fibers per millimeter squared, all the way up to well above 10 in some cases. And so how is this accomplished? Number one, improved fiber coating technology. Number two, bend insensitive fiber. So G657.A1 has the high mode-field diameter and is backwards compatible with G652D. It's very similar to the G652D type fiber, but some tweaks here and there to improve the bend insensitivity. And then if you're looking at a really high packing density as an example for the fiber itself, you may be looking at more of a low mode-field diameter. That could either be an A1 type or an A2 type. The A2 has a little bit more of a little bit different of a preform/refractive index design to it that allows for improvements on the bend and sensitivity aspect. Another bullet point here is reduced fiber coating. So the traditional or the legacy diameter has been 250, but you can see how we're slowly progressing to smaller diameters. 200's typical, but now we're talking about going below that, 180 or maybe even lower. So the issue there, though, is you're going to have the lower diameter over, lower fiber diameter. You're going to be dealing with more fiber breaks, in the factory. So then that carries costs associated with that. But the intent is to have a, fully vetted fiber within the cable prior to installation and operation. And then just a couple other bullet points here. Just improved processing technology, whether that be from the tubing stage where applicable all the way through to the jacking stage of the cabling process. So very precise cable production permits the smaller dimensions, anywhere from the tube all the way to the jacket, like I said, depending on what the construction is of your cable. So looking at this from an application standpoint, what's your right microcable solution? So there's a variety of questions that could be posed here. But considering infrastructure and labor is absolutely critical before selecting the right cable. So some questions that may be posed: what infrastructure is already available? What's your right of way? What environment are you installing? Are you installing in an urban environment, or are you installing it in either a suburban or rural environment? And what are the equipment and labor? What equipment and labor is required for the installation? Then lastly, if you're going in, maybe you're looking at the labor itself. What's available in terms of the skill set, wherever you're maybe installing it. Also looking at vaults, pedestals, and closures. So size is definitely a consideration. So some scenarios in which you may want to consider microcable. Like off to the left here, there may be a multipath microduct already installed, and then there may be some empty spaces or empty slots in which you can install additional cables. Microcable specifically. And like I mentioned, maybe you're dealing with a very congested area, like an urban area, and microduct and microcable may be the perfect solution for that. And another scenario I want to touch on is perhaps there's already a duct installed, and it's large enough where it can either occupy, there could be another, there could be a microduct installed within that duct or conduit, or alternatively, you could do overblowing with the microcable that you have selected. So moving on to fiber count. So overall cable fiber count specifically. So maybe you just want to install just enough capacity for the demand that is there in a certain area. So that comes with the lowest cable costs. So it comes with smaller cable, vaults, closures, etc. So the issue there, though, is you may run into, like I said, you may run into capacity constraints where if you need to add more fiber, you're going to have to go in and do a new installation. On the flip side of that, maybe you want to look at installing the maximum fiber count now. Adding fiber is inexpensive in the grand scheme of things. You do have the future capacity in the ground. You're going to have a higher cable cost. And maybe you're going to be dealing with larger vaults and closures depending on exactly what was selected. And somewhere in the middle would be adding a little bit of capacity, but you could also be using more of a legacy or more of a, the typical fiber type and design. So for example, here, 250 micron G657.A1, and that would be, like I said before, backwards compatible with a legacy G652D type fiber. due to the lack of mode field diameter mismatch. So not the least expensive, not necessarily the most flexible, but that could be your happy medium. And so some of the pictures that I have here, the middle one is a 288 fiber cable inside of a 1410 duct, a 7.4 millimeter cable diameter. And then the right picture here is half the fiber count, but at a 7.8 millimeter diameter or cable diameter, also carrying the same duct size, but you can see how there's a little bit of a difference there in terms of capacity or that can be utilized. Moving on to the next slide here, looking at the FTTH split architecture, centralized versus distributed splits. Advantages of centralized, you'd be dealing with lower electronics costs. If your optical line terminal ports wasted for the centralized split, then you'll also be dealing with easier maintenance and troubleshooting. On the flip side, with distributed, you're looking at possibly using lower fiber count cables, smaller ducts, closures, handholds, etc. Less splicing. You can also avoid cabinets. And so for a typical application on the centralized split, you may be looking at high density areas or lower expected take rate relative to the distributed split. And then the typical use case for distributed would be medium to low density areas such as suburban or rural, and then MDUs, where you're doing the second split on the premises. So as a product development engineer, what do I look for in terms of developing new cable designs? So to start us off, you have the cross-sectional view of a cable in the middle, as well as the orange, which is the duct itself. And you do have a little bit of a gap here to allow for pressurized air to help with the forward movement of the cable itself. And so number one, I'm looking maybe at the duct fill ratio. And what I look at is the cable diameter, the outer diameter of the cable, and the duct inner diameter. And that ratio, I would like that to be around 0.8 or lower to help to ensure that the performance of the jetting the cable is optimal. The next thing that I maybe look for is the cable to duct friction. Whether you're playing around with the parameters of the duct itself, maybe you have like a ribbed lining or a special coating on the within the duct itself. But as a product development engineer on the cable side, I'm maybe looking at the jacket material, or I'm looking at minimizing the contact area of the jacket, whether that be for a traditional loose tube design. If you ever look at a microcable, you kind of see that rifling. And then another thing that another way to play around with that is also adding grooves to the outer jacket as well. And some in the industry are definitely taking advantage of that as well to ensure that the friction is minimal between the two, and so that helps with jetting performance. Then another thing that I may be looking at is the cable stiffness itself. So for a traditional loose tube design, you'll have a centralized compressive or tensile strength component in the middle. The tensile strength of cable is a good parameter to check. You can easily check that using a standard tensile bench testing protocol. But then if you're not looking at a traditional loose tube design, you may be looking at a unitube or a central tube design where that strength component is moved to the periphery. And so there's some games that need to be played there to ensure that the jetting performance, as before, is optimal. And just one thing that's worth pointing out here is we do have a white paper that will be provided with at the end of this webinar. And our team did a wonderful job of outlining some of the stuff that we're doing and some of the recommendations when you're doing an installation from a jetting perspective. So continuing on with that, so some of the different considerations, maybe looking at the fiber itself, what type am I using? Am I using 200 micron or 250 micron, or maybe even smaller than 200 micron? What kind of fiber am I using there? And also the level of bend insensitivity. Whether you're using a G657A1 type fiber, as I've mentioned, or if you need to go to a very high packing density, you may need to enlist the use of A2 type fiber, where you have high bend insensitivity, very good performance in that regard. And then what is your overall cable fiber count? And then if you're looking at a loose tube type design, like the top cross-sectional view here, how many fibers per tube or per subunit are you looking at using? What I'll show in several slides, maybe within the next 10 minutes or so, you'll see that we use 12 and 24 for a brunt of what we, brunt of our offerings. But some in the industry may even go higher, 36 as an example. Fiber form factor, loose and ribbon. So your traditional loose tube, you're going to typically use loose fiber. Ribbon, what's becoming used more and more is the use of intermittently bonded ribbon. So the bottom picture here is a unitube type design with this intermittently bonded ribbon, or what we're calling IBR within HFCL. So you can see the two different generalized cable constructions, this unitube or central tube versus the loose tube type configurations. And then continuing looking at loose tube, gel filled versus dry. So we'll talk about that later on in the presentation, and then maybe looking at playing around with the tube materials as well. In a traditional loose tube, you're going to be dealing with PVT in this type of scenario, but there may be some other opportunities to employ different materials, and that's another thing we'll touch on later. The compressive strength elements, the type and positioning, and also the interaction with other components. So the type, you may be using the traditional FRP or GRP, but there are scenarios in which aramid reinforced plastic or polymer, maybe that may make sense for the application. Then the positioning, touched on this a little bit, the central location for loose tube, and then the periphery for like a unitube type construction. And the positioning is very important, especially for the latter, because you want to ensure that there's minimal preferential bending. So if you're going through if you're blowing through a complex jetting route, if you have any sort of preferential bending, you may see some serious degradation in the jetting performance itself. And then lastly, the jacket itself, which provides environmental protection and just mechanical robustness to the overall cable itself. So there are some games that can be played there, playing around with the different jacket materials, and also the jacket surface. We touched on that a moment ago. The performance standards in the industry dedicated to microcable. So Telcordia GR20 core, that's your typical US standard for general purpose and light duty OSB cable. It may not be 100% suitable for small microcables, but it does out-reference IEC 60794-5-10 as an informative reference. And but more recently, ICEA has come out with their standard, which is purely dedicated to microcable. Initially published in 2016 with they do revisions every 5 years or so. And there's a little bit of a reduction in performance requirements, relative to GR20. For example, the tensile strength is going to be reduced to 1 times the cable weight per kilometer, which is more than suitable for a blowing type application. And then on top of that, compression impact, maybe some other performances that are also reduced relative to GR20. But then again, you're dealing with microduct. You have that mechanical protection provided by the duct itself. And then lastly, the IEC standard here. So this is the international standard for microcable. It's a little bit, you declare some of the performance there. There are some specs that are listed there as well. But yeah, just giving you an idea as to what's out there in terms of the performance requirements. And if you're more than interested in looking into this, feel free to go jumping into the standards, which can be interesting. Slide 11. Oh, pop quiz. So at this point, we'll shift over to question or I guess pop quiz, I guess question number 1. Okay, so which of the following are use cases for high fiber count, high density microcable? A, multipath microduct has been installed, but there are only 1 or 2 empty ducts left. B, construction is planned for a congested area, and microduct plus microcable allows minimal disruption. C, overbuilding occupied duct either through installation of a microduct or by direct overblowing, or D, all of the above. So I'll give you about 30 seconds or so. So I touched on this a little bit earlier in the presentation, and hopefully looks like a majority are answering it correctly. And so about 30 seconds in, so I think, yeah, D, all of the above. So those are a few different scenarios in which microcable and microduct may make sense for the application. So I think moving on to the next question. All right, so what is the primary function of the protective outer sheath in microcables? A, to enhance signal transmission. B, to provide mechanical strength, durability, and protection against environmental factors. C, to reduce the cost of cable production. Or D, to improve the flexibility of the cable. So this would be the primary function. I'll give another about 30 seconds or so. And similar to the last question, looks like a majority are answering this correctly. Yep, well done, everyone. Yeah, so B is the correct answer, to provide mechanical strength, durability, and protection against environmental factors. Moving on to the third one, which of the following is not typically a specification parameter of microcable or for microcables? Didn't really touch on this, but you'll see, let's see, where is it? But I'm sure you could deduce based on what's provided here. A, fiber attenuation. B, tensile strength, B, tensile strength, and C, temperature service window, or operating temperature range. Or D, color variety. Give another 30 seconds or so here. Yeah, so again, this is not typical, which not typically a specification parameter for microcable. Give it maybe 5 more seconds. Yeah, so color variety is not typically a spec used when designing and developing a microcable, although there may be some sort of customer requirement. Maybe the customer wants a certain jacket color, as an example. But as far as the overall cable performance is considered, fiber attenuation, tensile strength, temperature service window are a few of the parameters that to which we design and operate these cables. So moving on to number 4, the fourth question. What is the primary function of compressed air in the cable jetting process? A, to cool down the cable during installation. B, to create a force that contributes to the forward movement of the cable. C, to clean the duct or conduit before cable installation, or D, to increase the tension on the cable. Yep. So again, what is the primary function of compressed air? The pressurized air. Ten more seconds or so. Again, primary function here. So looks like a majority have answered this correctly. So it is to help create a force that contributes to the forward movement of the cable. So well done. Final question before we jump back into the presentation itself. How does cable jetting contribute to community satisfaction during infrastructure projects? A, by extending project timelines. B, through increased construction noise. C, by minimizing environmental and social disruptions. Or D, increasing the cost of public services. Yep. About 20 seconds or so. Yeah, so community satisfaction. There's a few of those that don't provide much satisfaction. I'll say that much. Okay, so yeah, C is the answer there, by minimizing environmental and social disruptions. So that's the advantage of using microcable in a jetting type application. So jumping back over to the presentation itself. So good job, everyone, on the pop quiz. So we'll dive into the specific cables that are out there within the industry and with a specific focus on HFCL. So focusing on the traditional loose tube microcable with gel-filled tubes. So this is a specific example, a 96 fiber stranded loose tube design. Off to the left is a standard, what we'll call a mini cable, it's still a microcable, all the way down to the far right, which would be from our nano thin product line, a 4.6 millimeter cable diameter. And so how is this accomplished? Number one, you have the improvements in the manufacturing process. And then number two, the use of 200 micron fiber as opposed to 250 micron fiber. And so with regards to what we offer anything from 24 fibers all the way up to 576, and all are qualified to the requirements of ICEA 744 and the applicable portions of GR20. And when you get really small, some of the aspects of GR20 may not be fully applicable to the design itself. And then minus 40 to 70 degrees Celsius operating temperature range. And then the installation performance was vetted at our HFCL jetting track in Hyderabad, India. And looking at the kind of expanding this out, it's a little bit of an eye chart here, but these are the offerings of HFCL. So starting off with the top left is our standard microcable, all the way down to our extra thin, ultra thin, and finally our nano thin. So as you go down the column here, you'll see a decrease in cable diameter with respect to each of the fiber counts listed here. And then something that I guess I didn't touch on a moment ago is all these fibers are qualified with G657.A1 type fiber. So you have that backwards compatibility. And you'll also notice the transition from 250 micron fiber down to 200, specifically going from 12 fiber tube configuration to 24 fiber tube configuration at our extra thin microcable product line. And then the fiber counts listed here, 12 and 24 for the tube, and then all the different cable fiber counts listed throughout. And then the diameter, and then also the typical minimum duct inner diameter that's targeted for each of these designs. And considering that rough 80% fill ratio rule that I mentioned a little while ago. And last thing to note is the nanothin microcable did win in the Cabling Innovators Award in October of 2023 for just the high packing density that we've been able to accomplish with the inputs here. Last slide on the traditional loose tube with the gel filled tubes. These are just the jetting performance results for our nano thin, the smallest designs, and our ultra thin, which is our second smallest product line. The 96 up to 576 are shown here. The different cable diameters, and what you'll notice is, in some cases, for example, the 144 and the 432, the nano thin is able to get into a smaller duct size. And in the cases in which both the duct sizes are equivalent, you'll see a little bit better performance. As an example, the 288 goes 2,000 meters on the IEC spec jetting track in Hyderabad. It goes full 2,000 meters versus 1,700 meters for the ultra thin inside the same duct size. And on the bottom right, you'll see the graph outputting. It's a little bit hard to see here, but the pushing force, there we go, pushing force, the speed, and as well as the duct pressure. So a few different critical parameters in which, for the jetting process itself. Okay, moving on to slide 15. So we've talked about the PBT gel filled tubes. So what alternatives are out there in terms of the tube itself? So alternative number one, you may be looking at, you may be wanting or desiring a dry tube configuration as opposed to gel filled. So that helps with cleaner fiber handling relative to the gel filled type tube. And so how's that accomplished? It's accomplished in our design with a water soluble yarn as opposed to the gel itself. And then another alternative may be looking at the tube material substitution. So we have what we call micromodules, and instead of PBT, we have substituted an LSCH, a low smoke zero halogen based material that helps with the tube flexibility. So maybe some advantages there in terms of routing, during the installation process. And so some quick examples here. So HFCL, we have just single layer designs listed here, up to 72 fibers, 96 and 144 at the respective cable diameters here, 5.6 for dry tubes, 5.3 for micromodules, 6.7 at the 96 fiber count, 6.4 for the micromodules, then at the 144 fiber count, 8.8 and 8.2 for dry tubes, micromodules, respectively. So yeah, that covers just a quick, some quick alternatives there, and then looking at maybe how they perform with respect to each other in terms of the kinking performance. So dry tubes perform don't perform the best of the three, but they do still meet the industry standard per IEC 60794-5-10. So that kink diameter is 14 times the tube diameter. And looking at gel filled tubes, 4 times D. So a lot, some significant improvements. The gel helps with that kinking resistance. And the micromodule also has the same kink diameter, but we were unable to go really much smaller because of the setup itself. And if you look, it's kind of hard to see here, but qualitatively, the path is more circular relative, for the micromodule relative to the gel filled PBT tube. And another thing to point out is the micromodule doesn't have that same set. After going through the straining process, the PBT tends to have more of a, when you're kind of cutting the tubes out and everything and exposing them, you kind of see more of a spiral type path as opposed to the micromodule, which tends to be easier to handle, is really what I'm trying to get at there. But kinking resistance and just general handling performance, micromodule, gel filled tube, and then dry tube in that order. Shifting gears a little bit, looking at the outer jacket itself. So there's been a lot of headway in providing low friction microcable jacketing solutions. And so within HFCL, we do have our own polymer compounding facility in Hosur, India, which is near Bangalore. And so we tasked our group there to come up with a custom formulation to improve or optimize the jetting performance, specifically using an HDPE type material. So as far as a torture test to fully vet our jetting solution there, we did a jetting trial with a 10.3 millimeter 288 fiber standard microcable into 1612 microduct. So you can see that fill ratio is extremely high. So we're expecting failure one way or the other. And so the length, as before with some of the other stuff that I mentioned, is the 2 kilometer test track length using the IEC N by 100 meter test track. So commercial jacket versus our low friction jacket, the jetting distance is similar. However, the time to get to that distance and obviously the average speed is drastically different. So over 28 minutes for the commercial jacket, then over just a little over 23 minutes for the low friction jacket. And you can see the differences in speed there for the installation. And yeah, last thing to note is this is being deployed commercially now as of last month. Or yeah, that's a few days ago, basically. So number 2, intermittently bonded ribbon. Touched on this a little while ago. A lot of people or a lot of companies in the industry are going after this for microcable because of what it offers. And so intermittently bonded ribbon, like I said, we call it IBR. And you can, what that allows you to do is, or what it is just the intermittent connections you can see here on the on this slide between each of the fibers. And that allows for the ribbon itself to collapse, unlike legacy flat ribbon. And so you can see how this bottom right picture is a 1728 of a general purpose OSP type cable. But you can see how the fiber itself is able to, or the ribbon itself is able to take advantage of the full interior of the cable sheath itself, unlike flat legacy ribbon. And then the other advantage here is just the mass fusion splicing component as opposed to single fiber splicing. So you can see the drastic difference in time required for fiber splicing. And so as a quick example, what we have listed here is a 432 versus a 1728. And despite being a lower fiber count, it takes much more time to splice all of those fibers compared to the 1728, quadruple the fiber count. Okay, so moving on to the next slide. So looking at this from a blowing performance or jetting performance perspective. So the R&D trial that we have here that we conducted was a 12.2 millimeter central tube type design in a 1,000 meter 2016 microduct. And you can see a drastic difference in terms of the time it took for the different jacket materials. There are the different cable types with the different jacket materials. So the standard jacket only went 620 meters at 43 meters per minute, whereas the low friction jacket itself went to, our solution went 1,000 meters at 47 meters per minute. So you can see a drastic difference just in that regard. And then kind of cascading that to a full product line here, we have our design, which is a unitube type design, ranging all the way up to what we have listed here, 288 to 576 at the respective cable diameters, 9.8, 11.2, and then 12.8. Targeting the different duct sizes here, and then you can see the jetting performance, which is pretty good. But you can just see how you see the performance there relative to one another. But yeah, so the unit tube type design, you have the intermittently bonded ribbon in the middle. You have water blocking components, swellable tape here, the outer jacket, and then within the outer jacket, you have the compressive strength elements that helps propel the cable and have the jetting performance as shown here. So all cables meet the applicable requirements of ICA 744, and like I said before, Telcord EGR 20 where applicable. And then like before, -40 to +70 temperature range. And one thing that we do want to point out is that we did win, we are a winner in the 2024 Lightwave Innovation Reviews for this type of design, targeting the different duct sizes using intermittently bonded ribbon. Okay, moving on to the next slide, advantages and disadvantages of stranded loose tube versus our intermittently bonded ribbon. The fiber packing density, loose fiber within a loose tube configuration is going to beat out intermittently bonded ribbon. There's just a little bit extra in terms of the sheath specific for the intermittently bonded ribbon. And so you'll see a difference here of, in terms of the sizing there. The jetting performance, loose tube, you do have that centrally located FRP as opposed to the peripherally located strength components there. And so that does not, that the central location of the FRP is preferred in terms of the performance on the jetting side of things. And then the minimum bend diameter, loose tube is also favored here. Central core can indeed flatten and kink, given just the general nature of this construction. However, splice time and restoration time, the mass fusion splicing enabled by the intermittently bonded ribbon gives significant time savings. And then in terms of backwards compatibility, the loose tube, traditional loose tube will provide that in favor, over the IBR that we have listed here. And then the fiber management, the preference is on the IBR as well. And then when it comes to cost itself, it really comes down to the application, what fiber is used, what diameter. It really comes down to taking a look at this from an overall systems view. Then I just want to quickly touch on low fiber count microcable. So we've talked about high fiber count cables on the past 10, 15 slides or so. But just a quick touch on this. So some additional designs, you may want to look at low fiber count, so up to 24 fibers typically. Maybe you're dealing with a small duct size, and so the cable diameter here would be 3 millimeters as an example on the max end. Like I said, these are typical, so you could be dealing with larger cable diameters there, larger fiber counts. And you may be wanting to employ a fire retardant jacket as another example. But these are just some quick examples as to what's out in the industry and what we do specifically within the HFCL group. And so as far as constructions go for these low fiber counts, so the blown fiber unit off to the top right here, you can see an outer jacket, and then like an inner layer, and then the loose fiber. And then the unit tube microcable is an alternative where we have an aramid reinforcing between the two layers. And so that may, more than anything, that may help with if you want to do like a short pull of the cable itself. Not necessarily recommended, but the aramid may have some added advantage there over the blown fiber unit. And so as far as jetting goes, so here's a quick example of a 2.4 millimeter 24 fiber blown unit using our internally developed and manufactured low friction HDPE jacketing, specifically targeting an A5 millimeter microduct, going for a distance of 1,000 meters in roughly 10.5 minutes. And so you can see the graph down below showing this. So in summary, microcables are like hats. One size may not necessarily fit all. So it really comes down to the application. What infrastructure is already in place? What do you want to, or what are the considerations on your end as an end user? You have to weigh the pros and cons of really everything. Whether short-term system costs and speed, the civil works, your passive optical network architecture, installer labor / termination labor, then long-term system cost and speed, so upgradability and restoration. So, like I said, it really comes down to your application and what really details that you need to iron out on your end. And so we did touch on several different cable design considerations and specific offerings that are out there. So the traditional product offering would be your traditional loose tube type. But we have made a lot of advancements within the industry, and specific to HFCL, we do have the added tools of intermittently bonded ribbon that you can add mass fusion splicing to your toolbox, and then lastly, low friction jacketing. And that's not necessarily just specific to HFCL, but within the industry, there's been a lot of headway with all the different tools that are out there to take advantage of this application. And so with that, I will turn it back over to Sean for the Q&A session.
Well, thanks, Henson, for a great presentation on a really great topic. And also let me extend my congratulations to you for winning an innovation award. That was quite a lot of really great diversity of vendors submitted this year. Just let's get on with some questions here. First one is, in what scenarios should you not deploy microcables? Like you just were talking about, it's not one size fits all. No. Whether we're deploying here in the U.S., I mean, which I'll get to a couple scenarios that you mentioned too before, but or another part of the world. I mean, every situation is different. So yeah, let's talk about that a little bit.
Yeah. So when you're wanting to pull cable in, microcable may not be the best situation. If you need a really large, robust cable, maybe a general purpose OSP loose tube type of design may fit the bill. These shouldn't go aerially. Like lashing, for example. And then there's some cases where you may want to do mid-span access, and some of the very small microcables may not be suitable for that. So per FOTP 244, that may not be the best application for that. Typically, if you want to do mid-span access, you may want to have a larger cable itself, or whether that be microcable or just be loose tube, larger microcable or larger dry loose tube that's typically used in the industry. So just a couple examples.
Great. Since HFCL is pushing more into the U.S., it's a pretty pivotal time right now with the BEAD funding going on that program and lots of state and local government funding. One of the questions is your cable BA compliant? The Build America, Buy America compliant. I know that we've been seeing a lot of different announcements about that, and a lot of different vendors are want to get a piece of that, and for good reason. I mean, there's a lot. It's all to benefit everybody to get more broadband. But just curious, yeah.
Yeah, I mean, currently we're not BABA Buy America or Build America Buy America compliant at this stage in the game. But yeah, considerations are definitely being made. Currently not BABA. But everything's strictly made in India, and I don't know if I touched on this, but we are expanding into Eastern Europe as well. So,
okay. Well, maybe you could talk a little bit about the regional differences, versus Europe versus U.S. I mean, you mentioned MDUs and, of course, rural opportunities here in the States and in other places, but tell us a little bit about like how microcables are being kind of, I guess, leveraged or looked at in different regions, for broadband and fiber. Yeah, give us a little bit of an overview. I thought that might be good.
Yeah, I mean, so microcable really became extremely popular in Europe and slowly making its headway here. We like our big, I think a good example is we like our big F250 type cables here in North America. But here whereas in Europe, there's a lot of considerations in terms of congestion or congested areas, and so microcable has become extremely popular there. But we're starting to see it become increasingly popular in not just urban areas here in North America, but also there may be some rural considerations as well, just for all the savings that are that I showed here.
Right. Yeah, and of course, some of the rural providers don't have as much staff as, let's say, an AT&T or a big carrier, and maybe this could ease their installation pain, or maybe less labor. So it all sounds like an lots of good things that could happen. Here's another interesting question: have you seen more adoption of microcables in long haul applications? And this one question, this person is saying, we're looking at options to maximize fiber count on a long haul route. Is that something HFCL is looking at, or
yeah? Yeah, I mean, I think that's something that definitely could be considered. Like I said, we've talked about the traditional fiber types, the G652D or type G657.81 type fiber. But I mean, that's something that could be considered is maybe employing more bend sensitive fiber, maybe for a longer haul type application. So,
okay. And I'm just going to pick off a couple other things here, like MDUs. I mean, you kind of touched upon that a little bit, certainly here in the States and in Europe too. Certainly the very different markets. But I mean, do you see an advantage in using this kind of fiber for MDU situations? Because a lot of service providers want to get access to that, especially because it's more excuse me, you can get a lot of customers. And, it's more profitable potentially, I guess, for a provider. But just curious to see what your thoughts on that is, just to expand a bit.
Yeah. So we touched on that a little bit. One of the last slides, low fiber count, blown unitube or blown fiber type solutions. We do have our own product set, and then there are companies are making headway in terms of adding fire retardant jackets for going straight into MDUs. So that's something that we considered as well. So it definitely has its own fit within the that application space.
Okay. Here's another question, and you might have answered this, but does this type of cable exist for ADSS type installations? I think that's aerial, but
yeah, that's aerial. So generally, you want to stick with large ADSS cables for that, but there are some smaller ADSS type cables that may fit the bill. But generally speaking, these should strictly be for a blown type application. But there are definitely smaller diameter ADSS cables that may fit exactly what what the application is that's being asked here.
Okay. And I'm going to come back to something else. You talked about the labor issues. I mean, certainly, you just mentioned, rural providers and other providers that, I mean, we do have a little bit of a, in the U.S., new generation of people being trained to install fiber, because that's what we're going to need, whether it's in the rural areas, through the BEAD program, or just, the large carriers. I mean, we're going to need more of a labor force. I mean, can these types of products, make it, I guess, kind of make it more efficient if, you're building a lot of fiber and you're training a new generation, I guess, of new installers to kind of get this done? I'm just curious. Yeah.
Yeah. I mean, the big thing, I mean, it's, as far as installation goes, I mean, it's relatively straightforward. You put down ducts, and you can, there are multipath duct options that allow for future installation for, essentially on the, allow for an overall cheap system cost. And so, yeah, there's advantage there. And you're only installing, you're not going from pole to pole, you're installing from one end, going to the end of the duct or the conduit itself. So there's advantages on that. I didn't really include numbers or anything in my presentation, but there's definitely a lot of benefit to going this route as opposed to more of a general purpose type of cable.
Okay. Here's another question. This is probably more of a long haul thing, but the question is, do you have any plans for WDM compatibility for microcables? And maybe you might have touched this, but I don't know.
I would have to refer that to another expert within HFCL.
Okay, yeah, no problem. I guess maybe for another
Sure.
another discussion. Let's see. You also mentioned, environments like, the downtown, the congested, the congested areas, I guess what we would call it, the suburban, the urban downtown where there's, excuse me, probably a lot of old infrastructure. I mean, so these types of cables can help a provider with that. I guess, it could make it more efficient, I suppose. And, if you have clogged up ducts and you can, this will help with those kinds of situations. I was curious.
Yeah. Very congested areas. Like we talked about all the different cable types that we have, or all the different cable sizes that we have, and perhaps something on the small end using very small fiber and small diameter cable along with small duct that could help alleviate some of that congestion, and while also adding all that, adding the capacity that's required. So that's one reason why microcable is becoming the preferred solution in urban environments.
Okay, so here in the North America, I guess you're getting a lot of interest. I'm sure from a lot of existing and potential customers. To kind of I mean we I would imagine, because there's so much pressure on everybody to get more fiber out, more broadband out. How can you do it more effectively? And there's always the cost pressure, especially if you get a larger company. And of course, a smaller rural provider that can all, as I watch your presentation, I guess could really benefit from these types of approaches that makes it more cost effective, less labor, I suppose, et cetera, et cetera.
Absolutely.
Good. Okay. Well, we're running up against the hour here. Maybe you can just share some final thoughts, and we can wrap up and take it from there. And thank you.
Yeah, thank you, Sean, and thank you to the Lightwave team. And this is a great presentation, or a great conduit in which, no pun intended there, conduit in which is able to present microcable and show the strengths of the HFCL specifically. And so that we're going to see more and more demand of microcable in North America. And if there's any particular requirements on your end, feel free to reach out. I do have my email address here, henson.toland@hfcl.us. So if you have any more questions, or if there are any specific inquiries, feel free to reach out. I appreciate it, Sean.
Yeah, great. Well, no, thanks, Henson, for some great education here. And to the audience, I just want to remind everybody, thanks again for coming to the webinar. Certificate attendance will be offered, and you'll be able to access the white paper that Henson mentioned before, as well as the presentation material, so you can take a look and maybe have a discussion with your colleagues about this really interesting kind of this interesting topic as it starts to which sounds to me like it's going to really start evolving this year. Again, I just see so many opportunities of where HFCL could go, just here in the North America, of course, but then of course Europe, like you said, and lots of other regions that are in the midst of this broadband, I guess, revolution, as we all call it. But that's what we all want to get, but we want to do it cost effectively and do it efficiently. So I thank you for your perspective, and again, thanks to the audience and HFCL for being the sponsor of today's webinar, Faster and High Density Optical Microcable. Once again, you will be able to listen to this on demand after this is over. But again, I want to thank everybody for coming today. Thanks to Henson for his great perspective. I'm Sean Buckley, Editor-in-Chief of Lightwave, and hope everybody has a great day. Thank you very much. Thank you.